Hello everyone. See, Unit 5 covers two nonlinear data structures, that is trees and graphs. Now we'll look into trees data structure. These are the topics that are to be covered under trees. First we'll look into the differences between linear and nonlinear data structures. Then we'll see a few concepts of binary trees, where we'll look into the terminologies of binary trees, types of binary trees, binary tree representation, and binary search tree operations, that is traversal, searching, and construction operations. Finally, we'll end up with expression tree construction. Coming to the differences between linear and non-linear data structure. In linear data structure, the data items are stored in sequential order. Traversal is linear in nature and it is easy to implement compared to non-linear data structure. Examples are arrays, stacks, queues, and linked lists. Coming to nonlinear data structure, here the data items are stored based on hierarchical relationship among the data items. Traversal is nonlinear in nature and it is difficult to implement. Examples are trees and graphs. Coming to the definition, so tree is a non-primitive nonlinear data structure. You can also call it as an acyclic graph, and you can define trees as the data structure which represents hierarchical relationship between individual data items. Coming to the definition of forest, it is a set of disjoint trees. In this example tree, if you remove the root node, then it becomes a forest with 3 trees. Here A is the root node, and if A node is removed, then you are left out with 3 trees, disjoint trees. So this collection we call it as forest. Now we'll look into a few terminologies like what do you mean by a node, branches, degree of a node, out degree of a node, in degree of a node. Say tree consists of set of finite elements. These finite elements are called as nodes, and the lines, set of lines which connects these nodes, they are called as branches. And the number of branches associated with the node is called the degree of the node, and number of branches leaving a node is called as an out degree of that node, and number of branches entering the node is called as in degree of that node. Coming to the definition of binary tree, a binary tree is a finite set of elements that is either empty or is partitioned into 3 disjoint subsets. The first subset contains a single element called the root of the tree, and the other 2 subsets are themselves binary trees, which are called as left and right subtrees of the original tree. So remember, binary tree can be either empty or it can be partitioned into 3 disjoint subsets. The first subset contains the root, a single node which is called the root, and the other 2 subsets are again binary trees which are called as left and right subtrees. So this is the diagrammatic representation for a binary tree. A is the root node here, and this is the left of this A, it is the left subtree, and right, it is the right subtree. And below this you are seeing the diagrammatic representation for binary tree where the tree is empty. This is how we have indicated, it is null tree or empty tree. And if binary tree is having only one node, it will be obviously the root node. And here in the third diagram what you are seeing is binary tree with 3 nodes. First is the root, then left subtree node and right subtree node. And similarly here you are seeing the other example binary trees. So what you can observe here is, since it is a binary tree, at any level you check, each node is having maximum of 2 children. That's why it is called as a binary tree. Maximum of 2 subtrees for each node. Okay. So now we will see few terminologies with respect to this example. Root node, here A is the root node. Coming to the parents, A, B, C, E, F are called as the parents. Parent nodes will be having at least the out degree as 1, and children node whose in degree is 1, they are all children nodes. B, C, D, E, G, F, H, I are all children. And coming to the siblings, 2 nodes with same parent are called as siblings. Here D and E are siblings since they are having the same parent as B. B and C are siblings, they are having the same parent as A. And H and I are siblings, they are having the same parent as F. And coming to the leaf node, they are also called as terminal nodes or external nodes. And you can define leaf node as the nodes whose out degree is 0. Remember, the root node will be having the in degree 0, and leaf nodes, the last nodes or the terminal nodes or external nodes, their out degree will be 0. And these are the leaf nodes in this example, D, G, H and I. And the internal nodes are B, C, E, F, and you can also include the root node as the internal node, non-terminal nodes or internal nodes. Okay. Next, coming to again the definition of parent, child, root and leaf node. I'll quickly go through these definitions since I've already discussed in the previous example. A node is a parent if it has successor nodes, that is if it has an out degree greater than 0. This is called as the parent node. It should be having successor nodes, or with respect to out degree, if you want to define, you can define it as if the node is having an out degree greater than 0, then it is a parent. And child node, a node with a predecessor is called as child, or node whose in degree is 1, it is called as the child node. Coming to the root node, a node with no predecessor is called as the root node. Or with respect to degree, you can define it as a node whose in degree is 0 is called as a root node. And coming to leaf or terminal or external node, a leaf is any node with an out degree of 0. That is, a node with no successor is called as the leaf node, or a node that has no child is called as a leaf node. Coming to ancestor, this is how we can define ancestor. Node N1 is an ancestor of node N2 if N1 is either parent of N2 or parent of some ancestor of N2. So in this example tree, you can see A is the ancestor of all the nodes. We can say A is an ancestor of node B. Why A is an ancestor of node B? Since A is parent of node B. We can also say A is an ancestor of node D. Why? Since A is parent of ancestor of node D. That's why we can say A is an ancestor of node D. Like this, you can see few examples of ancestors on this slide. Coming to the definition of descendants, the nodes in the path below the parent are called as descendants. So all the nodes below A, they are called as descendants of node A. That is B, C, D, E, F, G, H and I. See, all these nodes are descendants of node A. So what are the descendants of node B? All the nodes below the parent in this path, they are all descendants of node B. That is D, E, G. These are the descendants of node B. Descendants of node C, it is H, F and I. Descendants of node F, it is H and I. So the nodes in the path below the parent, they are called as descendants. Coming to left descendant. This is how we can define it. Node N2 is a left descendant of node N1 if N2 is either the left child of N1 or a descendant of left child of N1. So in simple terms, you can say the left subtree nodes of the node are called as left descendants and right subtree nodes are called as right descendants. Okay. In this example, B is the left descendant of node A. Why? Since B is left child of node A. We can also say E is the left descendant of node A. Why? Since E is the descendant of left child of node A. That's why we can say E is left descendant of node A. For node A, which are all the left descendants, it is B, D, E and G. Right? For node B, which are the left descendants, it is D. For node E, it is G. Right? For node F, which are the left descendants, it is H. Right? Similarly, you can define right descendant. Node N2 is a right descendant of node N1 if N2 is either right child of N1 or descendant of right child of N1. So in simple terms, you can say the right subtree nodes of a node are called as right descendants. So few examples we'll see. C is the right descendant of node A. Why we say C is the right descendant? since C is right child of node A, right? And similarly for node F, which is the right descendant, it is I. For node A, it is C, F, H and I, which are the right descendants, right? So why we say I as right descendant of node A? Since I is the descendant of right child of node A, okay? Coming to siblings, two nodes having same parent are called as siblings. So here in this example, B and C are siblings since they are having the same parent A. Now we'll see level of a node. This is how we can define it. It is the distance of a node from the root. And remember, root node is at level 0. The first node in the tree, binary tree, it is the root node. The level is 0. And the next successive nodes, that is B and C are at level 1, D, E and F are at level 2, G, H and I are at level 3. The distance, you can, if you want to find out what is the level of node E, you can make a count of the branches. So two branches are associated with node E. We can say node E is at level 2. You can make a count of the branches from the root node to that particular node whose level is to be found out, okay? Similarly, node G, it is associated with 3 branches. So from the root till G, 3 branches are associated. We can say the level of node G, it is 3. Coming to depth or height of a binary tree, the maximum level of any leaf in the tree, it is called as depth or height of the tree. Here in this example, the level of D, node D, which are all the leaf nodes here, D, G, H and I. For the level of node D is 2, level of node G is 3, H is 3 and I is 3. So what is the maximum level here for the leaf node? It is 3. So the depth or height of the binary tree given is 3.